Your talk is about high Whitehead maps and polyhedral products and the relations among them. Okay, welcome.
Thank you. It's a great pleasure to be in my room and talk to all of you. I wish I was there with you. And I just want, before I start, to thank Victor in particular for everything he has ever done for me and for maths in general. And I definitely wouldn't be here where I am if there was not for him. So yeah, today I'll be talking about high Whitehead maps and relations amongst them. And that's joint work with now my ex-PhD students, George Simmons and Matthew Staniforth. And just on Sunday, 2 days ago, we met and they were complaining that they finished a PhD studies with me and didn't have an opportunity to go and visit Moscow. So yeah, I promised them to bring them to Moscow one day. Okay, so the motivation for this study was Whitehead products, classical Whitehead products that were introduced by Whitehead in 41, and Whitehead products were introduced as the attaching maps for the product of two spheres. Namely, if we start with two homotopy classes of maps, alpha and beta, and look at the classical Whitehead product, as I said, the attaching map to the product of two spheres in dimensions, say, P and Q, then the Whitehead product is defined as the map or homotopy class of maps from the P plus Q minus 1 dimensional sphere into X by going through the attaching map for the product of two spheres, followed by the wedge of our two classes alpha and beta, and then folding it down into X. Okay, so Whitehead products are interesting, and we know that in homotopy theory, the Whitehead product gives a pairing on homotopy groups, and that pairing equips the homotopy groups with the structure of graded quasi-Lie algebra. So Samuelson on one hand and Blakers and Massey on the other, looking at the Lie algebra structures and the existence of the Jacobi identity in Lie algebras, conjectured that the Jacobi identity should hold in homotopy groups. So if we take three classes, alpha, beta, and gamma, we can see that the Jacobi identity holds. So this is this kind of sum of commutators in homotopy groups of spheres. So although it was kind of easy to conjecture that the Jacobi identity exists, actually the proof is surprisingly difficult. And today, two classical proofs of the Jacobi identity in the homotopy groups are known as Nakaoka-Toda's proof that uses relative homotopy groups. And the other proof is proof given by Matthew Hera, who for the first time used triple Massey product to prove the existence of the Jacobi identity. Okay, so Whitehead products initially was, as I said, defined in homotopy groups, namely you're looking at a spherical map, so a map from a sphere into a topological space. But then Arkwitz kind of generalize that pairing or Whitehead product to an arbitrary suspension space. So if you are looking in the group of homotopy classes of map from any suspension into some topological space Z, then we can define Whitehead product of two such maps, alpha and beta, in the following way. So the Whitehead product will be going, the domain of the Whitehead product will be suspension X smash Y, which obviously is homeomorphic to the X join Y. So now if you're realizing that space as what we like now to call polyhedral product, if you want, so we can write the join as a con on X cross Y union X cross con on Y over their common subspace X cross Y. Then this first map, which is a crucial map, is given by simply collapsing coordinate spaces X and Y. So obviously once you collapse X in a con on X, that becomes the suspension of X, and Y goes to a point in the first factor, and in the second factor you have X going to the point, and a con on Y maps into suspension of Y. So by this mapping, we land into the suspension of X, wedge suspension of Y, and then we simply compose that with a wedge of the two maps we started with, so alpha and beta. And as in classical case, we continue by folding Z, wedge Z into Z. So this is again an interesting map, and the question would be also, are there identities or relations among such generalized Whitehead products? So one of the results that we know of another identity apart from the Jacobi identity came from the work of Hardy. So in 1961, Hardy generalized the Whitehead product by defining the exterior Whitehead product as an operation, again, on homotopy groups. So we are back at looking spherical maps. So we will take K maps from a sphere to some space Yj, and we will associate this exterior Whitehead product, so it depends in this case on K inputs, as a homotopy, as an element of the homotopy groups of the fat wedge of these codomains Y1 to Yk. And the idea essentially is the same as I explained in the first instance, namely, we are taking the join of all the domains, in this case of all the spheres, and we look at that join in terms, we can decompose it as a product of, oh, there is a mistake here, as a product of, let me just try to fix, so of the disks, and in one coordinate we would have a circle. So proceeding this in the same way as before, we would look at a common space of these subspaces, and that's the product of all the spheres that are the boundaries of the given disks. So if we collapse that product of spheres, what we end up having is a fat wedge of spheres in dimension d1 to dk. In the same way, because the disk, when you collapse its boundary, is mapped to a sphere. And when you collapse sphere, obviously it goes to a point. So that's how we get a fat wedge, because in each of these factors, in each of these summands, we have only one sphere and the rest are disks. Okay, and now fat wedge, if you want, is a functorial construction. So just applying on that fat wedge of these maps we started with, we would land into the fat wedge of codomain spaces, YIs. Okay, so Hardy showed that if we are considering these exterior Whitehead products, then he identified well, what we call now Hardy's identity. Namely, if we assume, in this case, we want to assume that our spheres, the domain of Fi's, are at least of dimension 2, because we want to have that the domain is a suspension space, a coid space. Then if we look at generalized Whitehead products, maps, sorry, F1 to Fk, where we omitted Fi, and then we take a Whitehead product of Fi and that generalized Whitehead product and sum through all these combinations when I goes from 1 to k, so we erase one factor at a time, then we get that this is equal to 0. There is a certain sign involved, but that's a technical part and I don't want to go into it at the moment. This Whitehead product, if you want, sits in the homotopy groups of what I call here Z, and we obtain Z by simply looking at a fat wedge of all the codomains where we are omitted the coordinate I, and then we wedge it with a codomain of the map Fi. Okay, so this is the generalization of the Jacobi identity. Namely, if we have only 3 entries, so F1, F2, F3, looking at this Hardy's identity, we recover the Jacobi identity. So one of the questions in the homotopy theory is, well, you can continue this process and you can define what is called higher Whitehead products. I won't be going today into that direction. And one might ask, you know, can we describe all possible identities between Whitehead products and high Whitehead products? And we are motivated by this Hardy's identity. So in other words, can we, in general, in homotopy theory, realize all the relations maybe coming from the Lie groups? So our goal for today is to look at the homotopy theory of polyhedral products and try to describe various Whitehead maps or high Whitehead maps into polyhedral products and see whether we can use the combinatorics of polyhedral products to help us determine some generalizations of the Hardy identity. Okay, so what is a polyhedral product? Well, it is a construction that to a simplicial complex K on M vertices and a sequence of M topological pairs, say X1A1 to XM to AM, associates a topological space, this is governed primarily by the combinatorics of K and taking into account the input coming from these topological pairs. in the following way. Well, you can consider that polyhedral product as a co-limit construction over the phase category of K. So namely, you're looking your simplicial complex, you take a simplex, and then if that simplex, you take the elements of the simplex, and then you're looking at a product of spaces such that if their coordinate is labeled by sigma, then you're allowing the whole space xi. If that coordinate is not labeled by sigma, then we are allowing only the values in the subspace. So this is sitting obviously inside the product of all xi's, and as I say, it is really governed by the combinatorics of K, because the way we are gluing these subspaces, we are gluing it according to the phase category. Namely, if you take that tau is a subsimplex of sigma, then you're gluing that subspace corresponding to tau directly by inclusion to the subspace given by sigma. Okay, so in categorical terms, we can say that a polyhedral product is a functor with respect to continuous maps of topological pairs and simplicial inclusions of simplicial complexes. Okay. Good. So as I said, like our aim is to study Whitehead products or high Whitehead maps in polyhedral products, and try to describe as many relations between them as we can. So to start with, we'll start with things that we know. We know the Hardy identity amongst the exterior Whitehead products. So we will first rewrite the Hardy's exterior Whitehead maps in terms of maps between polyhedral products. Okay, so what do we have? We said that an exterior Whitehead product goes from the join of domains of FIs, those are spheres, and we can rewrite that join in terms of polyhedral products by taking that the simplicial complex that governs the shape of the polyhedral product is the boundary of a simplex. So this polyhedral product recovers the join of spheres, and then we can see that that exterior Whitehead product is given simple as a map of these polyhedral products by its functoriality, by first looking at the maps of pairs from a disk and a circle into yi to a point that really represent this class Fi. So Fi, I'm identifying here a class with a map itself. So Fi would be a map from di sphere into yi. And if you want to write that in a relative terms, then you can see that this is just, we can represent it as a map between a disk relative to its circle into yi relative to its point. Okay, so now applying that our functor, that polyhedral product is a functor with respect to continuous maps of topological pairs, we have this induced map of polyhedral products, and that map coincides with the exterior Whitehead product defined by Hardy. Okay, so
Jelena, can you hear us?
yes, I can.
That's us, but we can't hear you. Sorry.
Oh, you can't hear me.
For maybe for the last 3 minutes,
Oh,
the sound stopped coming.
I don't know.
Mhm.
Can you hear me? You can't, obviously.
Just your mic is now muted.
I know I'm playing with it.
Yeah, but it still doesn't work. Yeah.
Let me try to. What can I do? Let's try like this. Zoom.
Да. У нас проблема. Yeah, there is a problem on our side, Jelena. So just please wait a second. There is. Сейчас, видимо. Может, ей в чат написать, что проблема? Теперь она, наверное, на него смотрит. There is a problem on our side, apparently. So please, please wait a couple of minutes. Yeah.
Okay.
Yeah. We are still trying to fix it. Yeah.
Okay. Oh, I cannot.
But yeah, that's
Yeah.
that camera is not supposed to be on. Yeah. You can.
Yeah. You can switch it off.
Yeah. But unfortunately, we can't hear you still.
Recording in progress.
Okay. Could you say something?
Okay, can you hear me? It's echoing from your side, but I don't know if you can hear me. Taras, can you hear me?
Yes.
Oh,
We
you
hear
can
you.
now. Oh, okay.
Yeah. You can continue. Now it's
Oh,
okay.
okay. Sorry, I was still waiting. Oh, we can hear. I see in the chat now. Sorry for that. Yeah, great. Where should I continue from? Whether you heard me or not, what I was saying is that we wanted to rewrite this exterior Whitehead products defined by Hardy in terms of polyhedral products, and we use the fact that any map, say Fi, from the sphere into some topological space Yi, has a representative. It can be represented as a map of pairs, topological pairs, and those topological maps of topological pairs, together with the fact that polyhedral products are functors with respect to continuous maps of topological pairs, induce a map between polyhedral products, and that map is exactly the map defined by Hardy as an exterior Whitehead product. Okay, so we have now those exterior Whitehead products written in terms of polyhedral products, and we can see that the boundary of a simplex in some way, we could say, governs the existence of an exterior Whitehead product. So having that in mind, we define the higher Whitehead map, so not high Whitehead products, but a high Whitehead map, as a map that sits in a homotopy classes of maps between the join of xi's into some polyhedral product of yi's. So in that way, we are generalizing the Hardy's exterior Whitehead products by not anymore looking at them as maps from spheres like these Fi's into Yi, but from any arbitrary suspension Xi into Yi. So having, for example, K maps Fi's from a suspension space into some Yi, again we can represent them in terms of maps of topological pairs, which would then induce a map between polyhedral products. So that induced map between polyhedral products we will call the higher Whitehead map of F1 to Fk. Okay, and the idea is the same as before. We have that this space here is nothing else but the join of x1 to xk, but then we write these polyhedral products as using just simply the definition of them as the union of a simplicial complex k of cx1 cross cx2, and then in the ith coordinate, for example, we have xi, and all other coordinates are cornices on appropriate spaces axes. So all of these partial products will have a common subspace that is the product of these xi's. So collapsing those xi's into a point, we can define this high Whitehead map. Okay, so oops, sorry, I'm pressing the wrong computer. So high Whitehead maps have been studied in the homotopy theory of Davis-Januszkiewicz spaces, so a particular example of polyhedral products. And we have real nice results from Abramian and Panov, and as well as Zhuravleva, who used algebraic techniques or methods such as Grbić map and Adams-Hilton models to study high Whitehead maps in the homotopy groups of Davis-Janusz space. So just quickly, Davis-Janusz space, as I said, is an example of a polyhedral product in which all topological pairs are identified by CP infinity, infinite dimensional complex projective space, and the subspace we are taking is just the base point. Okay, so relevant examples for us are when we have a K that is, to start with, let's say, just two disjoint points, in which case Davis-Janusz space is CP infinity, wedge CP infinity. And then if you recognize these two disjoint points as the boundary of one simplex, then you can generalize this construction by looking at the boundary of an arbitrary simplex, let's say of dimension m-1, in which case we have m vertices, and Davis-Janusz space corresponding to the boundary of a simplex would be then just a fat wedge on m copies of CP infinity. So the Whitehead product that has been studied is concerned with the maps, these mu's. So that's just the bottom cell S2, the cell S2 that is included into CP infinity as the bottom cell. So obviously then a Whitehead product, high Whitehead product of say mu1 to mu k of k such inclusions would be sitting in the 2k minus 1 dimensional homotopy groups of Davis-Janusz. And Semyonov and Taras showed in 2017 that there is a very nice combinatorial criteria when these high Whitehead products are defined in the first place and when they are trivial. Obviously, as a high Whitehead product, they are not always defined. But if we are talking here about Whitehead products into the Davis-Janusz space, if the underlying simplicial complex K contains the boundary of simplex on those K vertices, then Whitehead product is defined, and Whitehead product is trivial. Being a secondary operation, the Whitehead product is a set of homotopy classes that satisfy set properties, and for it to be trivial means that one of these maps inside the set is null homotopic. So not all of them obviously are null homotopic, but just one of them is null homotopic. And Taras and Semyonov showed that that Whitehead product is trivial, namely contains that null homotopic class, if and only if the whole simplex over the boundary of the simplex is contained in that underlying complex K. Okay, so we have a very nice description or characterization of the existence of Whitehead products and their triviality full in the terms or in combinatorial terms. Okay, so that's what we wanted to mimic, and instead of studying high Whitehead products, we are studying these high Whitehead maps that are given in terms of maps of polyhedral products, and they are actually elements of the high Whitehead product that you could define of these maps F1 to Fm, and we want to see whether we can find relations between them and whether these relations can be somehow tied to the combinatorics of simplicial complexes K that are underpinning the structure of polyhedral products. Okay, so although I won't be talking about how we prove that at all. Our main tools are really following the ideas of the proof of the Jacobi identity that were introduced by Nakaoka and Toda, namely to obtain all the results that I hope I will summarize now. We had to go and define relative high Whitehead maps and then kind of bring that techniques into play so that we can show that there are identities between these high Whitehead maps. Okay, so the main difference in our approach is that we are really not looking only at spherical high Whitehead maps, but we are able to use this polyhedral product language to extend that to non-spherical high Whitehead maps. So the previous techniques that people use, like Taras and Semyonov and Elizaveta, as I said, they were primarily focusing on some algebraic techniques using Hurevich, for example, as a Hurevich homomorphism and Adams-Hilton model. So for non-spherical high Whitehead maps, that is kind of not really useful, because we can't talk about, for example, Hurevich homomorphism in this setup. Okay, so our approach is kind of more geometrical by looking at these concretely at these topological spaces rather than invariants that we can associate to them. Okay, so good. So we have this hardest relation between these high Whitehead maps, and we want to see, can we can rewrite every single this exterior exterior Whitehead map in terms of polyhedral products, and I showed you that. And now the question is, can we really express in terms of polyhedral products also each summand of the Hardy's relation, and can we put them together so that that identity is governed by some simplicial complex? And obviously we can. So each of these, if you want iterated exterior Whitehead maps, can be seen as a map into a polyhedral product over the skeleton, k-3-dimensional skeleton of a k-1-dimensional simplex. So in that case, we can, using the combinatorics of that skeleton, we can really completely reconstruct the Hardy's relation or the identity, and we would say that the skeleton of this simplex is the simplicial complex that carries the relation. Okay, so our first goal is to say, well, okay, now that we can rewrite that in terms of polyhedral products, can we generalize the Hardy's identity to maps from suspensions rather than just from maps from spheres? So we can, and we do that by looking at maps, as I say, from an arbitrary suspension into a topological space Yi, and they then induce as maps of polyhedral products these iterated, if you want, high Whitehead maps that are going from this suspension of, oops, there is a mistake here, K, this is K. This suspension of joints of x1 to xk to the skeleton, to the polyhedral product of Yi's codomains over that skeleton of a simplex. Okay, so again, using the combinatorics of that skeleton, we can find that there is a relation between these high Whitehead maps, and essentially is more or less the same thing as a Hardy identity. Here we're having just a permutation. The Hardy identity had explicitly a sign, and the sign is coming just from the fact that these permutations are over spheres, so we can boil the whole permutation down to plus minus 1, where in this case, where we are permuting some general spaces xi's, we need to keep the permutation. Okay, but that's a technical thing. So what is real improvement, as I said, is that we are obtaining the Hardy relation for non-spherical, for these high Whitehead maps of non-spherical maps. Okay, so this is the skeleton of a simplex is kind of an atomic complex that that carries a relation. So we are wondering, okay, so can we have a different type of relations, and can they be also seen combinatorially? Okay, so to do that, we recall a construction that to a simplicial complex on M vertices and M simplicial complexes associates another simplicial complex. And that construction is very much similar to a polyhedral product. The only difference in the definition is that instead of Cartesian product, we're using the join. And the main reason for that is that we want to produce a simplicial complex. And we know that if you take two simplicial complexes, I don't know, K1 and K2, their Cartesian product is not a simplicial complex. But in the category of simplicial complexes, join is the right products. Namely, if you take now K1 and K2, two simplicial complexes, and you join them, you obtain a simplicial complex. So this joint polyhedral product is defined in the same as I say as a polyhedral product, and the composition complex would be then just a special case of joint polyhedral product in which we are taking pairs of simplicial complexes. In the first coordinate, we put the biggest simplicial complex we can, so that's a simplex, and then we take just some Li subcomplex of a simplex. So taking into account these M pairs of simplicial complexes, then we perform this polyhedral joint product over K, and the complex that we obtain we call the composition complex. So okay, so now we know we have this is called atomic, the smallest, whatever smallest really means in this context, simplicial complex that carries the relation. So we have that skeleton, and we can obviously in an empty way recognize that complex is an example of composition complex by simply putting all these additional complexes L1 to Lm as the empty sets. Okay, so now we are saying, okay, can we propagate these type of identities by simply starting with our shape of the identity, namely the skeleton of a simplex, and propagate it by pushing into the complex these various L1 to Lm. So to do that, we recognize that the empty set is really just the boundary of a simplex. And to generalize it, what we're gonna do, we're gonna, instead of the empty sets, now put these higher analogs, namely we will take some simplices and take their boundaries. So LIs will be boundaries of particular simplices. And to do that, sorry, I'm on iPad rather than my computer. So here we go. So what we're gonna do, we'll start with our vertex set of the simplicial complex called TEM, and then we will take a K partition of it. Namely, we will partition the set of vertices into K disjoint subsets. And then we will, to each subset, we will associate to each subset, we'll consider that subset of vertices as vertices of a simplex and take its boundary. So that's what we are doing here. So to each subset of vertices, we are associating a simplex, and then we are taking the boundary of it. Now, taking the composition complex with respect to this atomic identity complex, we propagate it by taking Ly, L1 to Lk to be the boundary of these simplices that are associated to the partition pi. Okay, so by doing that, now we can consider any, oops, I didn't write that in the, so we will take our maps Fi's that are going from from suspension of Xi into Yi, and we can form our, oops, sorry for that, higher Whitehead maps, and see that there is a relation of this type that is sitting obviously then in the homotopy classes or homotopy classes of maps from suspensions or desuspension of joints of these Xi's into that polyhedral product of codomains associated to this propagated, if you want, identity complex. Okay, so here what is interesting is that you see that these, before we had a high Whitehead map in the Hardy's identity, and then just one of these coordinates is an arbitrary map, where now we are having that we have a high Whitehead map, and in other coordinates we can have just arbitrary maps whatsoever, and then we are taking high Whitehead product of that, and we are obtaining a new set of relations. So these entries of these maps are completely determined by the partition pi. So namely, if we have a set pi, then the first Whitehead product, the inner high Whitehead product map, sorry, that we are taking is a high Whitehead map of the complementary maps, complementary maps Fj1 to Fjqi, and then in the outer high Whitehead product, we have the high Whitehead product of these complementary and maps that are labeled by pi. Okay, so so that's our main theorem, that we can produce now many relations between these high Whitehead maps, and those will be also relations of higher Whitehead products, because as we know, if you're talking about high Whitehead products, that each high Whitehead product is a set of maps, and if we want to talk about relations between high Whitehead products, we are essentially talking about relations between elements of the set. So having these relations among these high Whitehead maps, we are essentially producing the relations between high Whitehead products as well. Okay, so having our approach, I'll give you a few examples, and then I'll probably finish because the time is coming. I should finish right now. Okay, let me just say quickly that yes, if our partition is a partition into singletons, we recover the Hardy identity. Namely, you can see that, for example, if you just have 3 points, disjoint points, that gives you the Jacobi identity. If you have an arbitrary number of points, then under this partition, then you're recovering the Hardy identity. Just to give you one non-trivial example, so if we look at a partition of what's this, vertex set on 4 elements, then our identity complex is this simplicial complex that is kind of 2 triangles glued together back to back. Then we recover, we obtain a relation of this form. Okay, so now I ran out of time, but we can propagate that further using a notion of substitution complexes. So we can produce a much bigger family of complexes that will carry more identities of these among these high Whitehead maps. So I'll skip that. So we have now a huge family of polyhedral products that support a relation, various relations. But what is very interesting is that we can recover also identities with repeated factors. Namely, if you are looking at say a bracket like this, a Whitehead product like that, you would say, well, can you recover combinatorially something like this? In all previous cases, each Fi was corresponding to a certain vertex in our simplicial complex. So if I repeat, say, one map F1, that would mean that I need to repeat a vertex, but vertices are not kind of multi-vertices, we can't repeat them. However, it turns out we can also control these Whitehead products combinatorially by looking at the identity complexes and folding them. So if we start with this simplicial complex that carries, for example, a relation, then we can fold this complex by identifying vertices 1 and 4 and obtain this complex 1, 2, 3, for example. And as a result, we will get relations in which high Whitehead products will have repeated entries. So by doing that, what we generalize is Elizabeth's result. So Žuravljeva showed that in homotopy groups of Davis-Janusz-Kevis space, looking at them rationally, and she was using, if I remember correctly, Adams-Hilton model to find out that there is a relation of this type. And what is important here to notice is that mu1 repeats within one bracket, and so we can recover this this identity integrally, actually, by simply looking at the identity complex, one of the examples I gave before, and folding, namely identifying vertex 1 and vertex 4, so that we obtain a new relation that is integral, which essentially recovers this when you rationalize this integral relation, you recover Elizabeth's result. We have an extra term but that extra term is coming from the fact that, well, it doesn't appear rationally because it is a two torsion term. I think I'll just stop now and yeah, thank you everyone. I don't know if you can hear me or not, but I'm finished.
Раз. Can you hear us?
Now I can.
And now Victor has a question.
No, it's not question. Елена, you
Yeah.
hear me?
Yes,
It
yes,
is
I do.
So, it is very nice to see you and hear you. Thank you very much for the nice talk. I'm happy that you work very active with your colleague, with your student. So certainly I'm happy with your result. Thank you.
Thank you, Victor.
So could you please show that the last relation on the higher Whitehead product which you obtained for this? Is it?
This one.
Yeah. Oh, this is a relation, right?
Yeah.
Because that's for this particular substitute or composition complex.
Yeah, I just illustrate that one just
Oh yeah,
because
that was
I
yeah
used
with
this motivation that comes from Elizabeth's result. Obviously, we can
yes.
construct
Oh yeah,
many of those.
she had some repetitions there, right? That with
Yeah,
new
that's
one.
what I'm saying.
Yeah,
So there
that's
is
what.
new
Yeah, now I
one
see. Now I see. Yes.
and new one
That's
here.
what I
Yeah.
wanted to hear. Yeah, I see. So that
Yeah.
you can recover this one in a more general context when you have just arbitrary polyhedral product, not necessarily that spherical one, right?
That's right.
You,
And
you have
it's
this
an
general
integral. This is an integral
integral version. Yeah, I see.
version. Yeah. And
Yeah,
as I said, like in her example, we have two summands, yeah, where we have
Right.
three summands. But the point is that this middle summand is a
Right.
two torsion element. So obviously,
Yeah. That's
rationalization
very nice.
disappears.
Yeah. All right. And do you have some kind of general idea when this torsion element appears? Like how it's related to having repetitions in this iterated Whitehead products? When you have a repetition of indexes, does it necessarily imply that some torsion element appears?
No. You
No,
can have many examples where you just don't have where you have repeated vertices, but the torsion doesn't appear.
No torsion. Oh, okay. Right.
In general, it's a really difficult question, to see whether an element is a torsion element or not. But we have examples where you can see for various kind of ad hoc way that maps in the summands in the relations are all non-torsion elements, for example.
Right. Okay. Yeah. Thank you.
One thing that is easier in some cases to show that they are non-trivial. So, for example, one of the problem you might have is when you fold a simplicial complex, then you might so you start with the identity complex and you write your relation. Now you're folding your complex. That means that in some entries will be identified depending on the identification in the fold. But once you start identifying, some of the summands become trivial. So one of the issues is to show that once you fold your relation, it doesn't become completely trivial. Yeah. So that's something we worked on also and gave some combinatorial description when they are trivial, when they are not. But the torsion part is it's tricky in general. But it would be really nice to have a good combinatorial control over the torsion elements as well. Yeah. But we don't.
Okay, thank you very much. Okay,
Yeah.
let's thank. Okay, yeah, thank you.
Thank you.
Now we have short break for 5 minutes before the second following talk. And also we have a poster session in the back side of this room. It's not too large, but very interesting, and you can see these posters in this room, poster session.